It's my pleasure to introduce Cheng Huang from University of Kansas that is going to talk about the third test suite, which is going to be about combustion application and in particular predicting the solution outside the training window and representing long-term temporal dynamics. Please.
Thanks, Tamasa, for having me here. So I'm going to talk about a third applications. The problem gonna be unsteady only, and the quantity that we are interested for the ROM to achieve is predicting the solution outside the training window, especially for long-term temporal dynamics. I can give you a little bit background here is that the problem we are interested, I'm from the aerospace engineer department, and there, in addition to like what Matt just described, is that another major focus for like aerospace is the propulsion, and in propulsion we have all these type of combustion dynamics going on. So in a lot of the engines or many of the propulsion system. And even though nowadays we are able to do very good LES simulations for this type of propulsion system, you can do rocket, you can do a gas turbine. I think this is one of the most recent application for that. And you can, if you're looking at the cost, it's not that big, but I want to draw your attention that the cost is per like turnaround time for this kind of engines. And usually for a gas turbine engine, the fan's going to spin very fast. It's not just one turn. It's going to be a thousands or like hundreds thousands of turns when these engines are operating. And if you time this to the CPU hours, so the simulation becomes like unreachable. And you definitely need to reduce all the model for that. Okay. And similarly, here is another example. I think that's one of the most advanced, the propulsion concept that actually have like two features here. One is the combustion, and one is a shock wave. So we call it as a detonation wave. So again, so it's gonna take a lot of like CPU hour just for 1 millisecond simulation, and obviously this type of thing requires like hundreds of millisecond simulation to make sure the engine is stable. So if you want to use LES for design, that's going to be very much impractical. This is why we will need the ROM for that. Okay. But the challenging is that if we're looking at the ROM or to the challenges to like apply model order reduction methods for the combustion application, the flow we are talking about here is like a highly transport dominated, and in addition, on top of that, we have like a multi-scale, multi-physics coupling, because this is basically a turbulent flow with combustion and also with acoustics, because usually these engines are operating at very high pressure conditions. And you either have combustion noise, which is oscillating in a low amplitude, or you have huge pressure oscillation when you run into combustion dynamics issues in this engine. So we want to have ROM to be able to predict all these phenomena. But again, this is going to be a challenging area for ROM because there are a couple of things, right? There's had not been that many applications. I know there are quite a bit of people working on compressible fluid problem, but not as many as in the incompressible regime. And there has been much fewer activities in the combustion flows here because that by definition has a lot of challenging features. It has like a first for combustion to exist, you have a huge gradients, okay, and there's a steep gradient in the temperature here, and this gradient is moving. We all know you can. I'm gonna show one example. You can think about this as like a linear advection problem. We all know that this is very challenging for model order reduction, and here you can think about that the combustion has like many. Like hundreds of these linear advection problems, and they are moving in all kinds of three-dimensional here. And another thing is the equation we are solving, which I'm also going to talk a little bit, is highly nonlinear and the stiff. This is another thing challenging for model order reduction. And with all of that, and the thing we are interested is because again, as I said, we probably are able to simulate for one turnaround time for this kind of propulsion system, but the idea is that we want to predict much longer into the future. So how do we gonna do that? So that would be like the major focus for the test suite. We're here trying to go beyond the training window. For example, we only train for 1 milliseconds right here, and we are predicting for the next 10 or hundreds milliseconds. Okay. And if I give you one example of what we can do now, here's some of you have already seen this animation a couple of times, but here is we have just applied a state-of-art reduced order model with Petrov-Galerkin methods, like using the POD as the subspace. And this is a 3D gas turbine simulation, and we are able to, you can see we are able to, here is where the training ends, okay? Within the training window, we are able to do very well. This is expected. But what we really interested is to go beyond the training window, and this is a challenging case. As you can see that once it's go beyond the training window, the ROM kind of smears out. So it's not able to follow this complicated dynamics as you can see in the full order model. Although we did pretty well in terms of the accuracy for reproduction within the training window and also in the dimension reduction itself, but there's very, very limited predictive capability beyond the training window. So that's the first thing. And if we think about the reason, I think it's pretty straightforward. The basis we are using, the POD is a linear subspace. It's not able to represent into the future. So no matter how fancy your reduced order model master is going to be, if the basis is bad, then you are not able to predict that as one of the reasons. Of course, there are a way to fix it, is that you by including more training data. But again, they're gonna including more training data, meaning there will be much more offline costs. So let me actually give you guys another example. So this is another example. I'm trying to answer the question that what is enough training data if I just want to predict some kind of interest, right? So for the real application, we are not trying to say I want to capture the for the model at every grid point and every time instance. That's actually not a very fair requirement for ROM. Because we want ROM for engineering design. So for design engineer, what they care about is, are you able to capture the trend? And are you able to give me the useful information, which is some quantity of interest? So one of the quantity of interest that they care about is the IMS, is the statistical quantity that quantifies like the fluctuation of some physical quantity. Here, I just pick up a temperature right here, and I'm saying that I want to see how much training data I'm going to require to capture 10 milliseconds of unsteady calculation, and then use that to calculate the IMS. Of course, if you have very wrong unsteady like predictions, then your IMS won't be good, right? So that will be the goal here. And just try to evaluate how much training data is required. And you can see the first thing you can do is that you include 2 milliseconds, 4 milliseconds, 6 milliseconds, and all the way to all the testing data you want to look at, all the way to 10 milliseconds, and then just do a straightforward POD on that. Of course, the more training data you have, the more capable your POD basis is going to represent. But on the other hand, it could be, if you can see here, if you look at the POD energy decay right here, that's actually indicating two things. One of the things Matt already elaborated pretty well in his talk, and we have the similar issue here for the combustion problem is the slow decay of a Congrove N width. So we have a Congrove barrier problem as well here. Even for the 2 milliseconds, you can actually see the decay is quite slow. In order to go to 99.9% of the energy, you're going to require 200. And you can see that if you want to use 10 milliseconds of training data, and which contains quite a bit of information, in order to get some accurate representation, you're going to require 1,000 modes there, POD modes there. Then that makes the ROM becomes unaffordable. Okay. Another thing, if you notice, is that there's no convergence of the low rank approximation versus the training data information. So what it says is that every time I want to predict the better into the future, I'm expecting if I including more training data, I'm getting better representation. for the next 2 milliseconds, but that doesn't seem to be the case here, because every time you include another 2 milliseconds here, the number of modes pretty much increase proportionally. Okay, almost double from like 2 to 4 milliseconds, triple from 2 to 6 milliseconds. It's pretty clear if you look at the 99.9% energy line here. So it's kind of a created dilemma. You want to predict getting better prediction into the future with more training data, but as you include more training data, you're barely include you're only including new information. But if you're trying to use that to predict the next future, then the next future is a brand new physics you haven't seen in your training data, and then so on and so forth. We are falling into a very deep rabbit hole there. So this has been the challenge we are facing now. And if we kind of further this study and then just using the projector for the model, so there's no wrong that this is only a projection of the for the model onto the basis we generated using different training data right here. You can actually see the issue here, okay? 2 milliseconds to predict 10 milliseconds, this is pretty much what we are expecting from the ROM, but you can see the RMS is pretty bad. And the 4 milliseconds, you can see some like in improvement. This is great, but not very much. 6 milliseconds seems to be getting closer, but again, you are under predicting the IMS magnitude a lot, right? Because you didn't follow the oscillation magnitude very well in the shear layer region right here. And not until 8 milliseconds, I'm going to say things are more or less satisfying. But when you go to 8 milliseconds, remember, the testing data is 10 milliseconds, and I'm using 8 milliseconds to actually predict only 2 milliseconds. So this is very, very expensive. Okay. So, because if I have the resources to run 80% of the training data, I don't mind to run another 20% just to collect that for the model, because it doesn't take that much more efforts, right? Okay. So, and these are the motivation we are trying to encourage the community to look at this type of problem and to see if there's any there can be any improvement here. For some reason there we go. Okay, my video works here. So of course we are not expecting to having everybody working on the 3D rocket engines as I show here. Of course, I'm not even showing a rocket engine here. This is a simple configuration with only one injector. We are not expecting everybody to work on that, but a lot of the challenging features that we see in 3D, I think, can be translated into this simple 1D problem. I'm going to go through the equation in the next chart, but let me just go through the physics a little bit. So you can see that the red line represents a flame, which is characterized by a low temperature region because you have reactants coming from the left-hand side. They get burned and then they turn into hot product on the right-hand side. Okay, so the temperature jump could be going from 300 Kelvin to 2500 Kelvin. So that's like a very, very typical scenario for the combustion problem. Okay. And also you have the heat reaction represented by that sharp kind of peak in that green line here. So this is where this indicates where the reaction happens. So the first thing is that we are trying to mimic like hundreds of advection, the flame advection problem in just this one-dimensional advection problem. And as I said, you will have like a pressure oscillations as well anticipated in this chemical in this propulsion system. So we are also imposing acoustic oscillations from the downstream. So the oscillation is imposed from downstream. We just simply perturb the pressure at a certain certain amplitude and the frequency. If you can see, this is a simple perturbation. We have both non-reflective boundary condition upstream and downstream, and we just let the wave go out. So we're trying to simplify this scenario a little bit so you don't have a lot of like reflection going on in the domain. But you can see still the dynamics is quite challenging. You have multi-scale problem depending on where you are in the flame. Okay, the hot zone showing a longer waveform and the like colder zone showing a shorter waveform just because you have different sound speed and the acoustic will travels like very fast in the hot zone and very slow in the cold zone. So this is, I think, pretty much mimicking the challenge in the 3D, and this could be, but again, this is a 1D case, so it's really a much lower entry level than this 3D problem. So if you're interested, we have a little bit more detailed descriptions under this link. And the equation we are solving is just 1D Navier-Stokes equation with the species transport. Yeah, I know there are a lot of terms here, and I'm going to go through a couple of them. So we are solving the continuity, momentum, and energy equation. This is like the conservation equation plus a species transport equation. So for this problem, we only have two species. So we devised a very, very simple, we actually created a very simple like chemistry model, so make it much easier for people to do. So you only have like 4 equations to solve, and with the viscous term and also with the source term. So we'll talk about the source term in a bit, okay? But one of the things I want to say is that, because I know combustion is a small community compared to the aerodynamics, so we are not expecting everyone to be expert in combustion and able to code up even this 1D problem, because they're going to take some time. We are actually providing the code. I'm going to actually talk about a little bit on that as well, but here is the equation we are solving. And even for the reacting flow model, for the reaction model, we are making things extremely simple. Okay, so you never seen a reaction happening like that except for some ionization reaction. I think it happened this way, but this is like the simplest model we can find. This is like, again, a two-species system. We're only describing reactant turning into product, okay? Of course, you don't have a lot of flexibility here, but again, we are trying to lower the entry-level barrier for everybody for the model reduction community as much as possible. And this is just only a one step, and we have everything made to be constant, every property, so you don't need to know a lot of the finer detail on how things are done doing in the 3D, but we're trying to make the model as simple as possible for this 1D problem. Okay, and this is the code that Michigan published, I think, this year. So this is a Python package for developing reduced order model for reacting fluid flow. So we have a code being put in the GitHub. Let me try to exit the presentation here. Are you still able to see my screen?
Yes.
Yes, great. So this is, we actually put the code here in the public GitHub right here. So you're free to download that. And again, the motivation that we want the involvement of everyone, but we're trying to reduce the development time for everyone for this reacting flow problem. So because not everyone again is like a combustion expert. Even for this problem, it's gonna take some time to code up a code that can run this type of physics. Okay, and have and have every little step here just to make things easier. In addition to the combustion problem, we do have two other non-reacting problems able to be set up from that, but I want to just focus on the combustion application today. So we also provide a little bit more detail on the governing equation, because I know there will be some like non-intrusive method people want to apply this type of method. Yes.
Sorry, Chen. I'm not sure if I'm seeing the slide that you're supposed to show, because I'm seeing some PowerPoint presentation with the Journal of Open Source Software. Are you showing that, or are you showing something else?
I'm showing something else. Okay. Oh, I see. That is why. Let me stop sharing this one. Okay, I think I need to share. Okay, how about now?
Yes, now I think it's
Okay,
better.
great. Okay. So
Thanks.
yeah, here, okay, then let me go back. Here is the GitHub that we put the code already there. So the code, again, this is a 1D code, a Python one, easy to set up, because I even give couple undergraduate students, just see if they are able to follow the instruction and run this code. I think overall it's a friendly code there. Although the code doesn't have a lot of other capability, but at least for the test problem we set up, it should be quite robust. And in addition to the code, we also provide all kind of the information regarding the PDE. So the governing equation, the flux scheme, because as I said, there will be non-intrusive methods. Developer wants to know what kind of equation you are solving and what kind of numerical scheme you are using. So that might be important to them. And if, again, if for some of the other people, they want to actually use their own code, make some modification, hopefully this type of information will be useful to them. So including the flux, including the boundary condition, time integrator, we all actually provide information there. So we have a separate wiki page for that. So that's what we have for this problem. Yeah. Let me stop sharing here and then going back to my slides. Okay. So and you can, as I said, that we have we encounter the same issue as in 1D, and the issue is more revealing than the 3D problem, because you can see that we have the same issue by increasing different number of snapshots. Again, this is the problem. Let me go back to that animation. So the problem here is that the flame is moving from the left to the right. This is a transient problem. So what we are trying to do here is that if you can include only a small portion of the training data, can we predict into the future? Okay, let's say the whole transient process goes from 0 to 45 microseconds. And we are trying to see if 15 microseconds or 25 or 35 microseconds of training data is enough. And again, you see the similar issue that you see in this 3D problem. Here we are evaluating the projection error just based on the basis you generated from these snapshots. Of course, the decay, the energy decay is not that as scary as the 3D, but again, this is only a 1D problem. You can see it takes about 100 moles or something to getting a set good decay in the POD energy. So it's still quite significant barrier there. And yeah, and you can actually reproduce the issue that I mentioned in the 2D in the 3D problem is that if you use 100 base ROM and this is the training period, if I want to use that and no issue capture the training period very well, but once it's trying to go out, we all know this is a very challenging problem for model reduction. There are many studies on this already. We actually use that as an internal tutorial training for the students, and also uh, use that to do the preliminary investigation for some of the method, because again, this case takes very little time to run, to collect the data and etc., and easy to get on for students purpose. So here are a couple of papers. It's just not the conventional model order reduction. We do have non-intrusive methods as well also tried there. And also, we also tried recently, I think we also tried something with the neural network in this paper. Yeah, it's just presented at the SciTech this year. And the method, I think one of the method I'm developing now, because there are the other method developed by other people in the team here, but the method I think is promising is using adaptive basis. Again, the issue with this problem is that the basis is not good enough. And the way we think about that is that we use adaptive basis. So we are just basically changing the basis as the reduced order model is going. So you can see the basis, the ROM is first able to go beyond the training window. This is the offline training window for the adaptive basis. And then it can also go beyond the training window for the static basis and all the way into the future. So this is kind of the performance improvement that we are looking at. Of course, that seems to be great because we didn't require a lot of the offline training, but for this type of method, you did put a lot of like a workload towards the online phase. So we'll talk about that. So we in the matrix in the metrics evaluation, I think I'm 100% with Matt. We do need to report both online and offline training costs just for a more comprehensive evaluation of the method. So I will talk about that a little bit. Yeah, the preliminary method that I think that we put together for this type of problem, just put that on archive here, is the adaptive method. And it's not just adapting the basis, we're also adapting the sampling points for the hyperreduction. But I don't want to go through all the details here. I will just leave it here for a minute. Basically, we still solve the ROM, and then we evaluate some of the information from the full order model equation residual. So here is the expensive part for this method, because you do need to go to your equation residual and evaluate something. So that will significantly increase some of the computation time for your ROM. But again, you are reducing the offline training time and significantly improving your predictive capability. So there's always like pros and cons there. Again, we need to look at the kind of the gains in a more comprehensive way. It's not just in the offline phase or just on the online phase. It should be a whole package, right? Yeah, because when you're designing something, you're designing something from the kind of time we need to account is like both, right? The design engineer doesn't care if it's reduction in the online phase or on the offline phase. It's the whole turnaround time that matters. And then you you use the information you evaluate from the forward model to evaluate the basis, to update the basis, and then update the sampling point. So that's basically the idea. Okay, and yeah, this is one of the cases from the testing we run from this paper. And we use 10 snapshots for the offline training and the online testing going for that 45 microseconds, which is 4,500 snapshots. The ROM is on the dimension of 5, and there's a couple hyperparameters actually matters for this type of method. I think it also applies for some of the conventional model reduction methods. Is how many points you are selecting for your hyperreduction. Are you selecting 1%, 10%, or even 50%? And specifically for this method, another hyperparameter is how often do you update your basis and the points. So it says another frequency here. Here we choose to update our basis every time step, but we choose to not update the sampling points because they're going to require some expensive evaluation of the equation residual I mentioned earlier. So we only choose to do that every 50. Okay. So you can see the results. It's not like perfect, but certainly it improves things significantly. The advection of the flame capture well, and also the pressure oscillate. There are some phase shifts that has to be acknowledged, but overall it's a good prediction of the dynamics. Yeah, but this is just one hyperparameter. I think one of the things I want to I think it's going to be important for the performance assessment. Again, I also have like a three part for the performance assessment. The first is obviously the accuracy. And let's just set up a testing data set that we want our ROM to predict, okay? And then assess the accuracy within this testing data sets. But in addition to just report one case, I think one of the things I would recommend is to report the accuracy over like different hyperparameter, over different number of modes or different number of sampling points you use. I think Matt touched base on that also. I'm 100% agree on that. So this is something, because that's not necessarily, we all know that if you change some hyperparameter, the performance of your ROM gonna be different. And either you are caring more about accuracy or more about efficiency. I think a more comprehensive reporting of that gonna help us to understand understand the methods better. Yeah. And another one is the online cost. So this is what I plotted here. Again, the online cost will be evaluated over the hyperparameters. Hyperparameter here is the number of sampling points you choose out of the number of total grid points you have. Of course, depending on the method you are using, this hyperparameter might be defined differently, but here is how we define it. We have n number of finite volume cells, and we are only selecting to evaluate the residual term, the nonlinear terms at like only a small part of that. And reporting this one over another hyperparameter. Again, this hyperparameters specifically belong to the adaptive method. So yeah, I think all of that, you can see that, of course, sometimes if you choose to not updating your sampling points, you get more efficiency gain, but you also lose accuracy. So there will always be some compromises there. So this is the online cost. The offline cost, unfortunately, I don't have a chart right here, but I think that it is important, right? Because I think the community often just report the online gain cost, but the offline cost is also important. Again, from the point of a LES combustion person, that I cannot afford running even 10 LES for a rocket combustor or for a gas turbine combustor. This is why you probably see the results I showed at the beginning a couple of times, because every year you don't get to run this many cases. So then that it really matters for me that if like how much can you leverage from the offline calculation. And I think one of the parameters I'm trying to recommend here is the number of training snapshots versus the number of testing snapshots. For example, the adaptive ROM uses 10 snapshots and they're able to predict 4,500. Roughly that metrics, but I think there will be some better definition there. But here's another idea, and combined online cost and offline cost should give us a much better idea on the method performance itself. Yeah. And another one is not it's certainly not recommended, but worth to consider is that if the ROM can provide the parametric predictive capability. As I said, the code imposes a pressure oscillation perturbation from downstream. So two of the natural parameters that we can think about for this problem is the frequency of your perturbation and also the amplitude of your perturbation. Is your ROM able to capture all of that? And again, what is the offline cost and what is online cost for that? I think all of that will be give us a much comprehensive understanding of the method itself. Yeah, I think I'm gonna stop talking, and this should be my last chart. And if you want to look at the other two test cases, the information is all here. Yeah.
Thank you very much, Cheng, for it's a very nice talk. And are there any questions? I mean, I guess I can start with one, just one curiosity. So, I mean, if I understand correctly, in your LES test case, so I mean, in your larger test case that you have at the beginning, do you really care about the entire field, or do you care about quantities of inches? And in that case, more precisely, if you have quantity of inches, can you envision some sort of filtered, so to devise equation for filtered fields, meaning you don't try to approximate the entire solution field, but you try to approximate, say, the field convoluted with some filter
Yeah.
of some kind.
Yeah, that's a good question. In some application in proportion, I think a kind of small, like a local quantity of interest, for example, a pressure transducer, that's going to be enough, or you can filter your field. But what we are talking about here is what if an engine go wrong? Because, for example, one of the issues that people had before is for combustion instability. So let me just zoom in here. So for that, you will need the whole information for the field, because if this kind of it is not like a common phenomena. You can think about this as a rare like event or something, but once that happens, that's gonna be catastrophic for your engine design. So you want to make sure that's not the issue. And when that happens, things gonna happen locally and then spread it out to your whole field very, very drastically. So you will need to have a understanding of what's going on in terms of the whole flow field physics and to change your design to prevent such things from happening. Yeah.
I see. Okay.